Let's go through an example of using Green's theorem to compute a double integral in terms of a line integral. So the problem is we're given a curve C, which is x to the 2/3 plus y to the 2/3 equals 1. So C is pictured here. It's this star-shaped curve. And we can see that C is closed, so it bounds some region, which we'll call R. So we'll call this R. And the question is find the area bounded by C, so we want the area of R. Now, we know from previous work that, of course, we can just use the double integral over R of 1 dA to compute the area of R. On the other hand, Green's theorem tells us that we can also write this in terms of a line integral as long as certain conditions are met, right? So in this case, qx minus py had better be equal to 1 for this vector field. But so we have this 1/2 out in front, and here the partial derivative of this with respect to x is 1, and then minus the partial derivative of this with respect to x is -1. And so I get 2 over 2 is equal to 1. So Green's theorem says that the integral over C of this very specific vector field, -yx over 2, actually gives me the area of the region that C encloses. So this is a useful trick to compute areas in terms of line integrals. So the work we have to do now is actually to just directly compute this line integral using a parameterization. So what's the parameterization of this curve? Well, the idea is that if I think about x to the 1/3 and y to the 1/3, then the sum of the squares of those is equal to 1. So that suggests using the standard trig functions, but the idea is that because first I have to take the cube root, so basically the cube root of x I want to be cosine. So that means I'm going to set x equal to cosine cube t, and the cube root of y I want to be sine. So that means I'm going to set y equals sine cubed of t. So then when I take these to the 2/3 powers, I just get cosine squared and sine squared, and so when I add them up, I get 1. So we need to know, of course, the derivative r prime of t, and it's pretty straightforward to see that essentially t is still this angular coordinate that works its way around the curve. So we really want t to be running from 0 to 2 pi. Okay, so what's the derivative? Well, we can just compute. It's just a simple chain rule problem. So we get 3 cosine squared t and then negative sine t. And then here we get 3 sine squared t times cosine t. All right, and so now we have to rewrite this curve integral in terms of a single variable integral from 0 to 2 pi. And then I have minus y times dx, so I get minus sine cubed times minus 3 cosine squared t times sine t dt. And so that actually gives me a positive 3, and then it's cosine squared t sine to the 4th t. And we'll save the dt for the end. And I have plus x dy, so cosine cubed times 3 sine squared cosine. So I get plus 3 cosine to the 4th t sine squared t dt. Okay, so this might look a little complicated, but actually just using some basic trig, we can simplify this integral dramatically, and this won't be a very challenging calculation at all. So the first thing to do is just to factor out the greatest common factor here, which is 3 cosine squared t sine squared t. And what we're left with is, in the first term I have sine squared t, and in the second term I have cosine squared t. So this is really useful because, of course, sine squared plus cosine squared is 1, so I'm just left with the integrand is 3 cosine squared times sine squared. All right, now what do we do with cosine squared sine squared? Well, sine of 2t is 2 sine t cosine t. So that means this product of cosine times sine is equal to sine 2t over 2. And since I have it squared, I can just square that. So in the end I have 3/2, the integral 0 to 2 pi, and then this integrand simplifies to sine squared of 2t over 4. So I have dt. Okay, so in the end I have 3/8. The integral is 0 to 2 pi. And then whenever I have just a single trig function squared, I can use essentially the half angle formula backwards, and I can write this as, so sine squared of 2t is 1 minus cosine of twice that angle, so 4t over 2 dt. And now we finally have a pretty basic function that we can just integrate. So the first 1/2 is going to give me a 2 pi over 2, so that's going to be 3 pi over 8, and then I have minus and the integral of cosine of 4t from 0 to 2 pi. Well, because this is a multiple of the period of this function, in the end this term will just contribute essentially 0 to this integral. So in the end, I'm left with this 3 pi over 8. And so we've calculated the area that's bounded by the curve C, this star-shaped curve, x to the 2/3 plus y to the 2/3 equals 1, is equal to 3/8. And again, the method that we used to compute this was using Green's theorem, which equates these two integrals. And so because for this particular vector field, which we of course chose exactly to have this property, the qx minus py for this vector field is equal to 1, and so this line integral in fact computes the area that's bounded by the curve C. And so this is another way to use Green's theorem, where instead of turning a curve integral into a double integral, we're in fact turning a double integral into a curve integral to, in this case, to compute an area. So and Green's theorem in general can be used in either direction. And this is a good example of that.